Good afternoon. Our topic for today is approximation using orthogonal polynomial. What are we approximating? We're saying, okay, if we are given a function or it's a set of data, then we're asked to approximate to into a power series. A power series. What do I mean? I mean something like y equal to a naught plus a1x plus a1x squared and so on. We've seen how we do this using the continuous least square method and the discrete least square method. So now we want to see how we can approximate our function, say y equal to f of x using orthogonal polynomials. Now to start with, what are orthogonal polynomials? Now two polynomials f of x and g of x are said to be orthogonal with respect to a weight function w of x over an interval a comma b if the integral from a to b of the weight function multiplied by the first function f multiplied by the second function g dx is equal to 0. Example, take f of x to be equal to x and g of x to be equal to 3x squared minus 1 over 2. And then we are saying we want to use the weight function. Suppose our weight function is 1 over an interval minus 1 comma 1. Then we can see that if we integrate from minus 1 to 1 of 1 times x times 3x squared minus 1 over 2 dx, we get 0. Since we get 0, we say that these two functions are orthogonal to this weight function over the interval minus 1 comma 1. So if that is clear, we want to find we want to approximate our function using polynomials like this. All right, so let y be equal to f of x be the polynomial we want to approximate, okay, and then let y equal to a naught phi naught of x plus a1 phi 1 of x up to an phi n of x be the polynomial we want to fit this y into, where phi I of x, I from 1 to n, are the orthogonal polynomials. Okay, so if this is correct, the residue of this function, the residue s of this is given as s equal to integral a to b omega x y minus capital Y all square dx. Remember, we said that for orthogonal polynomials can only be orthogonal to each other if there is a weighting function over an interval a to b. Okay, so your residue is given as integral a to b of that weighting function times y minus this polynomial we want to approximate it to power 2 dx. Okay, so we can as well say our s is equal to integral a to b omega x into y minus a naught phi naught of x plus a1 phi 1 of x up to an phi n of x all square dx. Remember, we said our phi values are the orthogonal polynomials. Of course, a naught, a1, a2, up to an are constants to be determined. All right, so we want to get that thing that minimizes the residue. So to minimize this residue, we say a particular ds, the ai should be equal to 0. Where i is a number between 0 and n. So where 0 is less or equal to I, less or equal to n. Now let's take this step by step. Let's start with the s, the a naught, so that we can see how the s, the a I will behave. So we said our residue s is giving us integral a to b omega x into y minus a naught phi naught of x plus a1 phi 1 of x till it gets to an phi n of x all square dx. So we want to get the s, the ai. So let's start with the s, the a naught, so that we can see how I will behave. Don't forget, your I is a number between 0 and n. So if a behaves a way, I too should behave that way, because they are all following this same pattern. So at the s, the a naught, since our a naught here is the variable, then every other one becomes a constant. So your w is a constant, your y is a constant, every other thing becomes constant. So we have this one to be equal to minus 2 integral a to b omega x phi naught of x into y minus a naught phi naught of x plus a1 phi 1 of x up to an phi n of x dx. So if we continue like this, we can get to our ds, the ai, which is what we need in particular, and then it will be minus 2 integral a to b omega x phi I of x. Just change our 0 to I, so times y minus a naught phi naught plus a1 phi 1 plus ai phi I. Remember we said our I is between 0 and n. So this continues again till it gets to an phi n dx. Remember we said we want that thing that minimizes the residue. So we want our ds, the ai to be equal to 0. By implication, we have minus 2 integral a to b omega x phi I of x into y minus a naught phi naught plus a1 phi 1 plus ai phi I plus an phi n dx equal to 0. By implication, we can do it with our minus 2. So we have this to be integral a to b omega x phi I y minus a naught phi naught plus a1 phi 1 plus ai phi I, then it gets to an phi n. Now remember, from our basic knowledge of integration, we know that integral a into b minus c dx is equal to integral ab dx minus integral ac dx. So here, if I'm saying this is my a, this is b, and this is c, then I can have ab dx minus ac dx. So that the integral there becomes integral a to b omega x phi I of x times y dx minus integral a to b omega x phi I of x into a naught phi naught of x till it gets to an phi n of x. This, and then it should be equal to 0. Now whenever we have a minus b given us 0, it means that a is equal to b. So by implication, we can have this to be integral a to b omega x phi I of x y dx equal to integral a to b omega x phi I of x a naught phi naught till we get to an phi n dx. Of course, again, we can expand this integral. I'm saying a into b plus c plus, so we can say it is ab plus ac and so on. So here we can have all of this to be equal to, this implies that integral ab omega x phi I of x times y dx should be equal to integral a to b omega x phi I of x a naught phi naught of x dx plus integral a to b omega x phi I of x a1 phi 1 of x dx. This will continue till it gets to I. So we have integral a to b omega x phi I of x ai phi I of x dx, and then till it gets to n. So plus integral a to b omega x phi I an phi I dx. This is what we have. So now remember, we said that two polynomials are said to be orthogonal with respect to a weight function if, so we said for orthogonal polynomials, the integral from a to b omega x phi I of x phi j of x dx should be equal to 0 if I is not equal to j. That is, if these two are different, then it should be 0. But we'll be having it to be integral a to b omega x phi I square of x dx if I equal to j. This is very, very logical. I'm multiplying these two, so it becomes phi I square. But when they are different, we get 0. So it means that if we go back to this previous line, every other thing we have here will be 0 apart from where we have phi I. What do I mean? Already our a naught here is a constant. So you can come out of the integral. So I'm saying phi naught. I and 0 are different. So the guy will be 0. So I will be having this to be 0. Here again, I'm saying I and 1. It will be 0. So every other thing here too will be 0. This one here will stay because it is I and I. Here too will be 0. So it means that our result should be we should be having integral a to b omega x phi I of x y dx to be equal to ai integral a to b omega x phi I square of x dx. Now, what is the goal of everything we've been doing so far? Remember, we said our y should be of the form a naught phi naught plus a1 phi 1 up to an phi n, where all these phi are orthogonal polynomials. So basically, they are known polynomials. The only thing we don't know here are these a values. So the goal of this proof so far has been to get our a values, so get a naught, a1, and so on. So from here we can deduce that our ai should be equal to integral a to b omega x phi I of x y dx over integral a to b omega x phi I square of x dx. So this is the goal of everything we do. So we have to get this ai, so that when I is 0 we can get a naught, when I is 1 we can get a1, and so on and so on. So please let us note this and hold it. Now we've been saying orthogonal polynomials. We've been dealing with phi since. How do we get this polynomial? Now there are 4 orthogonal polynomials. There are 4. So orthogonal polynomials and their weight functions. Okay, so we have one, the legendary polynomials. The legendary, its weight function is 1 and the interval is from -1 to 1. Number 2, we have the Chebyshev. Its weight function is 1 over square root of 1 minus x squared, and its interval is from -1 to 1. Number 3, we have the Amite. Its weight function is exponential minus x, and the interval is from 0 to infinity. Number 4, we have the Laguerre. Its weight function is exponential minus x squared, and the interval is from minus infinity to infinity. Okay, so for this course about the legendary and the Chebyshev polynomials. So let's go and see how we get the phi naught phi 1 for legendary, phi naught phi 1 for Chebyshev. For legendary polynomials, to get the polynomials themselves, we use what we call the Rodriguez formula. The Rodriguez formula. Now, what does this formula say? This formula says that to get phi n of x, we say it is equal to 1 over 2 to power n factorial, the nth derivative of x squared minus 1 to power n. So we are saying that to get phi naught phi 1, we just replace our n with 0, 1, and so on. So when n is 0, our phi naught of x will simply be 1 over 2 to power 0, 0 factorial, the 0th derivative of x squared minus 1 to the power 0, which is 0. So our phi naught is, which is 1. So our phi naught is 1. 2 to the power 0 is 1. 0 factorial is 1. All of this is 1. So we have our phi naught to be 1. When n is 1, we can get phi 1 of x, which will be 1 over 2 to the power 1, 1 factorial, the first derivative of x squared minus 1 to the power 1, which will give us 1 over 2 times 2x, and that is x. So our phi 1 for the legendary is x. When n is 2, phi 2 of x will be equal to 1 over 2 squared times 2 factorial, the second derivative of x squared minus 1 to the power 2, which is the same thing as 1 over 8, the first derivative of 4x x squared minus 1. And then finally, I can now say it is equal to 1 over 8 into this is 4x cubed. That will be 12x squared. We have 12x squared minus 4. And then that is 3x squared minus 1 over 2. So we can get more of this results. So we can get phi naught, phi 1, phi 2, phi 3, and so on. So one thing I want us to pick from here is that, particularly that our phi I, your phi I is a polynomial of degree I. What do I mean? Phi naught is a polynomial of degree 0, basically. So I have 1 x to the power 0. Phi 1, a polynomial of degree 1, x. Phi 2, degree 2, 3x squared. So phi 3 will be a polynomial of degree 3, and so on. So phi I is a polynomial of degree I. So this is for the legendary polynomials. All of this are all the polynomials we need. So let's even confirm if this polynomial really is orthogonal. How do we do that? We simply pick any two, and then we run it with the weight function and its interval. So we see if it is orthogonal truly. So let's pick phi 1 and phi 2. Let's pick phi 1 and phi 2. All right. So we'll be having integral minus 1 to 1 times x times 3x squared minus 1 over 2 dx, which will give us integral minus 1 to 1 3x cubed minus 3 minus x over 2 dx, which will give me 0. Why is it giving me 0? The integral from minus a to a of a function dx is equal to 0 whenever f of x is an odd function. Whenever f is an odd function. So it is enough for me to show that this guy here is an orthogonal polynomial. So the legendary polynomial is an orthogonal polynomial. So I'll be moving on to the Chebyshev polynomials. How do we get its own functions? How? So for the Chebyshev, we use the relation. We use the relation phi n plus 1 of x equal to 2x phi n of x minus phi n minus 1 of x, where phi naught equal 1 and phi 1 equals to x. So if these two hold, we can go and get phi 2, phi 3, and so on. So when n is 1, here I'll be having this to be phi 2 of x equal to 2x phi 1 of x minus phi naught of x. And that will produce 2x times x minus 1, which is 2x squared minus 1. So our phi 2 for Chebyshev is 2x squared minus 1. You can get phi 3. When n is 2, we get phi 3 of x to be equal to 2x phi 2 of x minus phi 1 of x. And that will be 2x into 2x squared minus 1 minus phi 1 is x minus x, which produces 4x cubed minus 2x minus x, which is the same thing as 4x cubed minus 3x. So we can say that here also your phi I is a polynomial of degree I. So phi 3 is a polynomial of degree 3. Phi 2 is a polynomial of degree 2, and so on. So these are the polynomials we are considering in this case. Let's take an example. Find the legendary linear and quadratic least square approximations to f of x equal to exponential x on the interval minus 1 to 1. So we were told to find a legendary linear and quadratic approximations. So for our linear approximation, it is enough to say that our y should be equal to a naught phi naught of x plus a1 phi 1 of x. Why? We said our phi I is a polynomial of degree I. So phi 1 is a polynomial of degree 1, means that this whole thing will be a linear function. And then for degree 2, you can take it to a1 phi a2 phi 2 of x, and so on like that. Of course, we are aware that for legendary, our phi naught of x is equal to 1 and phi 1 of x is equal to x, as agreed earlier. Okay, so we need to get a naught and ai. Recall, we said that our ai is equal to integral a to b, the weight function w of x, phi I of x, y dx, over integral a to b, omega x, phi I square of x dx. So when I is 0, we get a naught to be equal to integral. Of course, our a to b is minus 1 to 1. Weight function is 1 for legendary. Then phi I here becomes phi naught. So that is 1. 1 times our y here is our function, which is exponential x. So exponential x dx over integral minus 1 to 1. Weight function again is 1 times phi I. We get 1 again. That's 1 square dx. So we have all we need. This gives us integral minus 1 to 1 exponential x dx over integral minus 1 to 1 dx. So from here, we have this to be exponential x from minus 1 to 1 over, this is x from minus 1 to 1. And then this produces exponential 1 minus exponential minus 1 over 1 minus minus 1. So if we use our calculator, we get this to be 1.1752. So this is our A naught. Can then proceed to go and get A1. So our A1 here will be our A1 in this case will be integral minus 1 to 1, again weight function, that's 1 times, now we have phi 1, our phi 1 is x, so 1 times x, then times our y, exponential x dx, over integral minus 1 to 1 times phi 1 squared, that's x squared dx. And then from here we have this to be integral minus 1 to 1 x exponential x dx over integral minus 1 to 1 x squared dx, which produces in our calculator here, when you integrate and then you use your calculator, you get this to be 1.1036. 1.1036. So it means that the linear approximation of exponential x is given to be y, which is supposed to be a naught phi naught of x plus a1 phi 1 of x, will then be our a naught is 1.1752, phi naught is 1, plus a1 is 1.1036, phi 1 is x. So we have 1.1752 plus 1.1036x. So this is the linear polynomial that approximates y equal to exponential x using the orthogonal polynomials. So the second phase asks us to go and get the quadratic polynomial that approximates this. So it means that we need to get a particular A2. So once we can get the A2, we can combine with what we know already, and then it produces that polynomial. So our A2 will be integral minus 1 to 1 times phi 2. Our phi 2 in this case, we said it is 3x squared minus 1 over 2. Remember, for a legendary polynomial, then times exponential x dx over integral minus 1 to 1 times 3x squared minus 1 over 2 all square dx. And then if you integrate all of this and then you use your calculator, you will have your results to be 0.3578. 0.3578. So therefore, the polynomial that approximates to the degree 2 exponential x is giving us y equal to, remember, a naught phi naught plus a1 phi 1 plus a2 phi 2, which will be a naught is 1.1752. So we have 1.1752 times 1 plus a1 is 1.1036 times x, then plus 0.3578 times 3x squared minus 1 over 2. And then if when you do your algebra and then you simplify this whole thing, we get this to be 1.1762 plus 1.10. No, you can simplify this and get your results. You can simplify, but this is my final results. If you ask me,